Hello everyone. In this video, you will see how to decide an improper integral, converge or diverge by using a compression test. So this is the theorem that we are going to use, an exercise. Assume we have a functions f and g, real valued integrable functions. And we have this condition 0 smaller than equal to fx, smaller than equal to gx, for all x's bigger than certain number a. That is the lower boundary of the integral that we are talking about. So if gx, if this integral converges, then the integral fx also converge. If the fx diverge, then the gx diverges. What is the idea behind this is this. So you think about, you have a series of A, B, C. If your series C converge, because that is the bigger one compared to the series B, and if this converge, if it's going to be focused on in some places in the infinity, then definitely series B will do the same. So if series C converge, then the series B converge. On the other hand, the series A is smaller than the series B. If series B diverge, because it's smaller, if up to the infinity, it will go larger and larger and cannot be decided whether it is diverge to something, then it makes the series B diverge because series A is smaller and diverge. So series B has to be diverged. Similar behavior needs to be seen in the both series. So this is all about in the summarized in this theorem, right? Because G is the bigger than F. If G converges, the integral, improper integral related to G converges, and the improper integral of the F converge. Why we are thinking of the series is we know that definition of the integral related to with the infinite sums. Okay, I think this is clear in that moment. Let's do some, before we start doing an exercise, let's do another proposition, because in order to be able to use this compression test, it will be a handy, this proposition will be very handy to know, because we want to know some improper integrals in our hands so that we can compare. Right? And then consider this, this proposition states that this improper integral converge if p is bigger than 1 and diverge if p is smaller than or equal to 1. This is pretty straightforward to prove it, and this is a proof here. If, for example, let's go through quickly. If p is not equal to 1, then this integral, as limit r goes to the infinity from y to r, x to the minus p dx, then this integral will be 1, of course, the power, the integral of this rational function will be that the power will be plus 1, and then this constant number will come up to the coefficient plus 1, and similarly this will be the x to the minus p plus 1. So that is the integral of this quantity, and then we need to put the boundaries in, this boundary minus this boundary is substituted in this entity, that give us this. So when r goes to the infinity, let's call this entity is I. If p1 minus p is smaller than 0, then that will be is 1 over p minus 1. That makes the I converge. So this converge if 1 minus p is smaller than 0. If 1 minus p is bigger than 0, that in the limit will be infinite. So it diverges. If p is equal to 1, then we need to look at the situation in a different way. Then if p is equal to 1, this integral will give us ln x. Then we have ln r minus ln 1. ln 1 is equal to 0. When r goes to the infinity, ln r is infinite. Then I diverge. So these are all the conditions as I summarized here. This integral converges if the p is bigger than 1, and this integral diverges if the p is smaller than or equal to 1. Okay, this is a handy proposition that we can use for comparison test. Okay, let's do an example. Question is whether this integral converge or diverge. Okay, we need to find something bigger or something smaller that we can apply the comparison test. So ln x is smaller than n, x1 over n minus 1 for n bigger than 0 and for all x bigger than 0. So this is a fact. Let's use this fact. And by using it as fact, ln x divided by x3 over 2. So basically, I am multiplying this with 1 over x3 over 2. Since this is the boundaries from 2 to the infinity, x is bigger than 0 already here. So we are considering the x's between 2 to the infinity. In that range, I can do that. X is not equal to 0 in that range. So I can multiply everything with the 1 over x to the power 3 over 2. So this is how we get from here to here. Then you have a 1 over n here. We have x3 over n here. We can organize this as x3 over 2 minus 1 over n. And we are leaving this as it is. So minus 3 over 2, 1 over n is basically 3n minus 2. I'm multiplying this by n, this by 2. So that is 3n minus 2 divided by 2 to the n. For n is equal to 3, we have 9 minus 2 over 6, which is 7 over 6, which is bigger than 1. I want to find out the number. I'm thinking why I'm doing that. I'm doing that because I want to make a similarity for this part. So I found something here bigger than of this function for all x's in that range. And then I want to be able to use the proposition which converge, it says converge when p is bigger than 1. So if I take the n is equal to 3, this is true for all n, and n is equal to 3 is a number bigger than 0, which I can do that. And that will give me something which will be useful for me to use the proposition and to use the theorem. Okay, so ln x over x3 over 2 is smaller than or equal to n, 1 over x7 over 6 minus 1 over x3 over 2. So we can write n is equal to 3 here. But anyhow, by the proposition, this and this one converge because this number and this number is already bigger than 1. So both of them converge. Since both of them converge, this one is converged by the comparison theorem. So this integral converges. That's all we need to do for this. This is not a very straightforward example. So you can have many different failure attempts as well. So for example, if you want to wish to use the limit form of the comparison theorem, that is in my video on proper integrals too. And if you try, for example, ln x3 over 2 divided by 1 over x3 over 2, then you will find the limit of that is infinite. That is we were searching for a constant between 0 and infinite, but not 0, not infinite in this limit of comparison tests, and we cannot use that anymore, that theorem that we have in there. So if you want to use another inequality, for example, that will give you a failure attempt. Another failure attempt, you can see that ln x, if you want to use this inequality, ln x smaller than x minus 1 for all x bigger than 0, then if we try to do this one diverge, and even though this one converge. So the whole integral that fails as this diverge. So it is not a straightforward question. This is not a straightforward question, but if you use this inequality, that it will give you the answer, the correct answer. Let's do another example. Here, let's use whether this integral converge in this case. Use a limit form of compression test. See video Improper Integrals 2. We are going to use the limit form of compression. So let fx is 1 over root of it, that is the inside. That's the whole of it. And the gx is 1 over x cubed. If we look at the limit, then x to the 6 can be, I can write x3 as square root of x to the 6. It's exactly the same. So that is this entity, root x to the 6 minus 1. I can take the x to the 6 out in this equality, and they will cancel out. When x goes to the, I can take the limit inside the square root as well. So when x goes to the infinity, this quantity will be 0. Then only thing we will left will be 1. So square root of 1 is 1, which is a number between 0 and infinity. Then we can apply the limit form of compression test. That is, since this integral converge because of our proposition. What was our proposition? Let's see again. Any number, it doesn't mean that it's 1, but some number to infinity, 1 over x to the p dx converge when p is bigger than 1. So that makes this one converge. And since this is converged by the limit of the compression test, our integral converges. So these are the two examples by using the compression test. That's all I want to say in this video. Thank you very much for watching.